This is a video walkthrough of the Math 143 practice packet for the semester 2 final. So here, this first problem, it says solve this equation for b, simplify your answer. So in other words, we want to know what b equals. Notice it's a whole lot of fractions. What I like to do is I actually just like to get rid of fractions. So this one's going to require showing lots of work. So let me set up my workspace. I'm going to multiply everything by a to get rid of this a on the denominator. I got to multiply everything on the left side and everything on the right side. And then that cancels out. That one. I'm going to go ahead and rewrite my problem. So just when you multiply with the fractions, I can really make it a over 1. So top times top, that'll just be 2a, and it'll just stay a b on the bottom. Same thing over here, that'll be 2a, and just a c on the bottom. Now I'm going to go through and do that again and get rid of b on the denominator. So I'm going to multiply everything by b. I got to go over to this side and multiply that side. I started to multiply this right side. I need to multiply over here as well. Multiply everything by b to cancel that one out. And then I get 2 times b. Instead of b times 2, we like to put 2b, or 2 times b. This one is now 2a. And then this one over here becomes 2a with a b. 2a with the b. Of course, this one still has the fraction, so divided by c. I'm going to do it one more time, and I'm going to get rid of the c now. So I'm going to times this one by c. I'm going to times this one by c, and I got to times this one by c. Everything gets multiplied by c. These cancel. That was the whole point of it. And then actually, that's pretty much what I have. With those gone, it pretty much looks good. Let me rewrite it though. So we got 2bc on the left over here. And then now we have 2 pieces over here, but there's no more fraction because that is gone. So we have 2ac, and then we have 2ab. And there we go. Now again, our whole mission though is to solve for b. We want to know what b equals. The problem over here now is that I have a b in this piece, this part of the expression or the equation, and I have one over here, this term of this whole equation. So I have 2 different b's in this problem, and we don't like that. What I'm going to do is I'm going to get them both to one side so I can deal with it. Since this term has b and some stuff, and this term has b and some stuff, the problem is they're on the opposite sides of the equal sign. So I'm going to leave this other term over here that has nothing to do with b. I'm going to leave it on that right side. So I'm going to get rid of this term that has a b. I'm going to subtract it from both sides. Gone. Now as I rewrite it, these 2 things don't really combine. They kind of have some similarities, but they're really just 2 different unique things. So I'm going to start with the 2bc, and I'm going to subtract the 2ab. That is my new left side. And then the right side is just 2ac. Okay? So now, I'm going to kind of get rid of this dotted line here, that wall that I drew for my left side, right side. Now I notice over here, they both have a b multiplied into it. What I can do is, I can factor that out. I can take that b right here and that b right here, and I can just factor it out, pull it out, suck it out of there, and then they would both come out front as a package together. So it's b times both of those pieces. See how this has a b times it, this has a b times it? It's going to be b times all of it. And what's left over is the 2 and the c here. And what's left over here is just the 2 and the a. So I factored it out. I basically undistributed it. I could distribute it back in, or I could just factor it out. There's the right side. Now I can get b by itself. It's just b times all that package, that group. So I'm going to divide both sides by that whole group. And then we are going to get b by itself. So there we go. b is going to equal all that stuff. I'll just scoot this over a little bit so I can continue my work off to that right side. We're going to have that b is equal to all the stuff over here on the right side. So it's 2ac all over this whole expression, which I'm going to wrap in parentheses because it's safer to say that all of that is on the denominator. So that's what b equals. b equals 2ac all over 2c minus 2a. That is my first answer. Now this next problem is very similar. So let's do this one a little bit quicker. Same idea. This time we're solving for y, so we got to get y equals. but I notice I have a fraction here. So I'll leave myself a little more room this time. Oops, not 2 times y, but 2 over y. Now I'm going to do my process of getting rid of these fractions. I'm going to multiply everything by x. I'll just try to do this a little bit quicker. I always like to do one of these at a time. Some people like to get rid of all the fractions in one shot, but just be careful. That can be dangerous. You can make a little mistake trying to handle lots of things at once. I just like to show my work here. Now I get rid of y. I just focus on one mission at a time. My mission right now is to get rid of the y. 1 times y is just y. That's just 2x, 3xy all over z. And now I can just get rid of the z. So times by z over here, times by z over here, and times by z over there. The whole point of that was to get rid of that one. So now I got yz on the left, and I got what? 2xz, and then what is this? 3xy, it looks like. Now again, what's my mission? To get y by itself, y equals. I notice there's a y, but there's another y over here. Of course, this guy doesn't have a y, so I'm going to leave that one alone. I'm going to get rid of this other piece on the right side that does have a y. The opposite of subtracting with that stuff is to add with that stuff. So that's gone. Now, I guess it really doesn't matter which one I put first here. I guess the yz was there first to begin with, so I'll leave it first, and then I'll put the plus 3xy. And then the only thing on the right side is this. I can't actually add those together, but what I do notice is, again, this piece, this first term has a y, and the second term has a y. I can factor it out since I'm multiplying in here with the y, and I'm multiplying in here with the y. Both of these individual pieces have a y. I can basically factor the y out and pull it out of both of those. So the y came from both of them, so that y belonged in here with the first guy, and all it would be left is a z. He also belonged in here with this guy, but all that's left is a 3x if I factored out the y. Now that it's y times all of that stuff, I can actually just divide both sides by all of that stuff. Looks like I forgot the parentheses there. So then, so we get y equals 2xz over the expression z plus 3x. I like to wrap those in parentheses so I know that all of that is on the denominator. And so that's my answer. I'll just kind of rewrite that y equals. And there we go. That's how we can do those two fraction equations or rational equations. All right, this one has 2 parts. Talks about solving this in interval notation. Well, first let's solve this. This is an absolute value equation, which actually means there's going to be 2 parts. I actually like to always imagine this as just saying the absolute value of x minus 5 equals 3. I like to imagine it says equals, and then I split it into my 2 parts. If you remember, absolute value had 2 parts. So let me do that. So I split it. This means this could be x minus 5 equals the positive 3, or x minus 5 could equal the negative 3. I should probably put the negative one on this side, just because negative is usually on the left. So I'll do that. This is the negative 3. Let me clean that up just a little bit. Just say the negative 3. So if I solve this negative 1 first by adding 5 to both sides, I get 2. I almost boxed that answer, but that's not quite my answer. I could add 5 to both sides over here on the positive one and get 8. So those are my 2 possibilities for when it equals 3, but the actual inequality here says greater than or equal to 3. So what I always do is create my sign line. And in fact, this even says draw a correct graph. This is going to be the graph of it. We got 2 answers. We got the answer of x could be 2 or x could be 8. That's when it was equal. We actually do want to equal, but we want to be greater than or equal to. So what we can then do is do a test point. We can test all these different regions and see which one fits this original inequality. 0, I could test 0 out. 0 would be over here. If I plug in 0, testing that out, let me switch colors to test it out. Testing that would be over here. I could say, maybe I'll put it on the bottom. I can say the absolute value of 0 minus 5, is that greater than or equal to 3? Of course, 0 minus 5 is just negative 5. And the absolute value of negative 5 is just 5. And 5 is greater than or equal to 3. This is the good side. This is good. Which means we actually could be equal to 2 because we could equal that thing. And then this side is good. Now, if you could test out the middle, but I'm going to anticipate that the middle is going to be bad. It usually goes good, bad, good, unless you have what's called a double zero or a double equals. Let me test the other side. So this could be good at 8 because that would make it equal to 3, which is what we want. But let's test the other side and see if it's also greater than. So let's test a number like 10. If I just think about testing the number 10, over here we tested the number 0. Let's use the testing in blue. So I could go 10 minus 5, but doing the absolute value of that, is that greater than or equal to 3? Well, that would be 10 minus 5 is 5. The absolute value of 5 is still 5, and that is greater than or equal to 3, so this is also the good side. So I would draw the arrow that way. Of course, in the middle, I could test a number in the middle. For example, like 5. I could test the number 5, and I'll do that, I guess, really quick, just to be sure. So if I plug in 5 into this original problem, the absolute value of 5 minus 5, is that greater than or equal to 3? Well, 5 minus 5 is 0. And the absolute value of 0 is 0. And that is not true. 0 is not greater than or equal to 3, so it was bad. So this is actually the correct graph. It says draw a correct graph of the solution set. This is the graph. Of course, you need the number line below it. You don't have to write the good and the bad, but you do need to do all of that. Now, what is the actual interval notation answer? We were supposed to do interval notation. Well, let's write that answer off to the side here. Inequality notation would be like this. It looks like that x could have equaled 2 or less than 2. Or x could have equaled 8 and been greater. Now this is inequality notation. Let's turn that into interval notation. Interval notation would be doing like an interval with a start and a stop for this interval, this region. So that would be going to negative infinity forever. In fact, I could have put negative infinity here on my inequality. And then, of course, it goes all the way up to 2, but it actually does include 2, so we put the bracket. Or, of course, for CWI, they like to use or using this, this union symbol. And so then this one, starts at 8, and of course we could equal 8, and it goes forever that way. We could have rewritten this one as 8 goes like this up to positive infinity. Of course, we usually start smallest to biggest, unless you just do the x on one side. And so this could have been going all the way to positive infinity. Now we don't do equals with infinity, so we always use parentheses. So the interval notation could look like this. It could also be written using that union here. Instead of writing or, you could do that union. That means you have to unite both of these possibilities because there were two different possibilities of where this could be the answer. Let's do another one. As I scroll up, here's another one a whole lot like it. So again, I like to think of it as being, what if it was just equals? Just think about that and let's solve it. If it was equals, I would of course split into two possibilities. It could have been the negative version or of course the positive version. I usually think of the positive version first. But I'm going to subtract 2 from both sides and we get negative 9 could have made it equal 7. And of course, here this would be what, positive 5. And so these are the two possibilities that would make it equal 7, but that's actually not what we want. We want to know if when it's less than 7, not even equal to 7. So that means for my graph, which, you know what, maybe I should do the graph in the graph spot. So I'll put the graph down here this time in the actual graph spot. So we could have got, what, negative 9 was an answer and 5 was a possibility. However, we don't want to equal those because we don't actually want to equal 7. We want to be less than 7. So these times, these two values, when x equals 7, we should put an open dot there. Now, some people know the quick way to tell that since this says we want this expression to be less than 7, then that's actually going to be in the middle because you want to be less than. You don't want to be greater than farther away going out. That's not what we want. We want to be less than, which is going to be in between these two spaces. And so we can tell this by, of course, just testing it out as usual. What's something in between here, a value we could test? Well, 0 is in here somewhere. 0 is probably closer over this way. If I plug a 0 into this and test it out, that would be 0 plus 2, the absolute value of that. Is that less than 7? Of course, 0 plus 2 is just 2. And the absolute value of 2 is still just 2. And yes, 2 is less than 7. This is the good space. And so we know that this is the space we want. You could test the other regions, but you're going to find out if you test it that this side doesn't work. That's going to be bad. And this side doesn't work as well. That's also going to be bad. So there is our graph. Our graph is technically the number line, the sign line here. Of course, you got to mark those two spots, and then you have to graph that. Now let's actually write the answer in interval notation. Remember, we need interval notation here. So our answer, we can use this graph, this picture to help us out. We want to be, it looks like -9 is the smallest, although we don't want to equal it. We want everything in the middle of that and 5. 5 is the biggest, but we don't exactly want to equal it. We want the x's in the middle. This is unfortunately inequality notation. We want interval notation, and that would just look like this. Parentheses, because they are not equal to, and we have our lowest limit and then our upper limit for this interval. So that is the official interval notation for this answer. Let's continue on. All right, this one. This one's an interesting problem just in how it's worded. So it says, describe how the graph of the function of this thing. Okay, so there's our function. How can it be obtained from the basic graph? Okay, well, what do they mean by that? Okay, we're going to start with just some function called log base 2 of x. Notice that's almost like this one right here. Log base 2 of x is just this piece right here. So what about this negative out front, and what about this 1/2 out front? What is that going to do to the basic graph of log? Even if you don't know what the basic graph of log is. Of course, we should probably know what the basic graph of log is. It actually has a vertical asymptote here at 0, and it actually climbs up like that. It's the inverse of an exponential. Now, what happens if you stick a negative out front? Well, it's going to flip this. What I like to do is, I like to just remember the good old days of parabolas. Parabolas is one of the first equations and functions that you actually mess with when you do this kind of stuff. So we had our good old parabola, and that was like y equals x squared. Well, what happens when you stick a negative out front? That just means you flip it. So, flipped. So that means this is definitely going to be flipped. It's going to be flipped. And then what about the 1/2 out front? Well, what happens if you take the good old parabola and you stick a 1/2 out front? Well, that's just going to change how wide it is or how narrow. We could say wide or narrow, or we could say steep and shallow. So this makes it wider, or technically we could even say shallower. Okay, so like a wider one for a parabola would look like this. It's wider or shallower. Okay, there's sort of two ways to think of it, wider or shallower. So let's see what this means for our logarithm. Of course, we could actually try and graph this new one on a calculator and compare it to the original and see how that goes. But let's see. Okay, so it's going to do what? So first, we'll start with this graph, and then it looks like it's blank by multiplying each blank by blank. What? Okay, let's look at the options we have for each of these things. So option A, is it going to stretch it horizontally, shrink it horizontally, stretch it vertically, or shrink it vertically? Now, when we look at this, how we describe the change of the parabola, the official way is to think of it as being shallower. It brought it down shallower. So we're actually thinking in the y direction. So it's actually not going to be the horizontal stuff. The official answer here is to shrink it vertically. That's going to be shrinking it in the up and down direction. It's going to be half as steep, so it's actually shallower. So this one is going to be shrink vertically. I know it also seems like it might kind of do some sort of weird stretch horizontally, but it's actually the vertical direction. And what is it? It says by multiplying each, what? Each we either have to say x or y coordinate. Now, technically, look at this 1/2. This 1/2 is actually multiplying with the x. It's going to multiply each x coordinate, and so that's going to result in a smaller y value. And so it's going to multiply each x coordinate by what number? We're supposed to write in a numerical value. Oh, it's multiplying it by 1/2. It's making it half as much, and that will become the y value. Same thing up here. I know I'm pointing to the parabola one because it's easier to look at. We're going to take whatever the log is, and we're going to multiply that value. We're going to multiply that. Actually, you know what? We need to redo this.